Hello everyone. So today we're going to talk about the instantaneous rate of change. Okay, so I'm going to first just give you a historical background, right? Because this is basically why calculus was invented, right? So a big why do we study calculus? Well, there's two main reasons. One is that has to do with the rate of change, and the other has to do with accumulation. Okay, so basically, I'm just going to pose for you this big question here. So, how do we find the instantaneous rate of change or the rate of change at an instant? Right? So, Isaac Newton, he's one of the men that invented calculus, was struggling with this question for a long time. Okay, he wanted to figure out the instantaneous velocity of an object at t equals, let's call it a, but some number, instead of the average velocity between 2 points, t equals a and t equals b. All right, so we knew how to find the average velocity, or in other words, the slope, for a very long time, but we didn't know, how could we figure out the rate of change at an instant, like at a specific point in time, not over an interval or in between 2 points, but at that specific moment. All right, so he started to answer this question by shrinking the distance between the 2 points and represented the distance between the 2 points by h. Okay, so he just took 2 points and he called the distance in between those 2 points h. And so, in other words, he started to compute the average velocity between 2 points, t equals a and t equals a plus h, for small h values. All right, so if I have a number line here, I'm going to call, here's my number line. This is, sorry, I don't know why I use this part, but here's my number line with some arrows here. So let's call this A. And then this is A plus H. So here what I'm saying to you is that this distance here between these 2 points is represented by H. Okay, and so I'll give you actual numbers so you can kind of see it a little bit better. So let's say I have 1 and then 1.5, right? So I could rewrite 1.5 as 1 plus 0.5, and then you guys would agree with me, right, that my distance between those 2 points is 0.5, or in other words, my h value here. Okay, so basically, I know this is super abstract when we're talking about a and then a plus h, and then that distance is h, but hopefully when I gave you actual numbers like 1 and 1.5, you saw that I could represent 1.5 as 1 plus 0.5, and then just say that the distance between those 2 points on the number line is 1/2, or 0.5, right? Okay, so what he was doing is he was shrinking that distance, so shrinking, those h values, making them as small as possible, and computing the average velocity, which we already know how to do. Okay, so let's do like an actual example. So in a time of t seconds, a particle moves a distance of s of t feet from its starting point, where s of t is represented by this function, 3t squared plus 1. And then I'm saying find the average velocity between the points t equals 1 and t equals 1 plus h for each of the following h values. Okay, so I give you different h values below. Then use your answer to estimate the instantaneous velocity of the particle at t equals 1. So I'm trying to estimate the instantaneous velocity using the average velocity. Okay, so let's do it for this first h value. All right, how do I write this? Well, I know that the average velocity I can say that this is equal to s of 1 plus h minus s of 1 all over 1 plus h minus 1. Okay, because those are my two t values, right? T equals 1 and t equals 1 plus h, right? So I'm representing my average velocity as s of 1 plus h, right? 1 plus h plugged into the function minus s of 1, and then all over those two t values, 1 plus h minus 1, right? Okay. And then now I'm just going to simplify the denominator. So I have s of 1 plus h minus s of 1, and then all over h, right? Those 1s in the denominator cancel there. All right, and now I'm going to actually plug in what my h value is. So my h value in part A is 0.1. So this is the same as s of 1 plus 0.1 minus s of 1 all over 0.1. So in other words, I want to find s of 1.1 minus s of 1 all over 0.1. Okay, and now I'm going to actually plug that into the function. So looking at what I highlighted in orange here. So s of 1.1 is going to give me 3 times 1.1 squared plus 1 minus, make sure you use parentheses, 3 times 1 squared plus 1, and then all over 0.1. Okay, and then now using a calculator, I get that this is 4.63 minus 4 over 0.1, which is equal to 6.3. And so at this stage here, I am using an approximation. Okay, so this is 6.3. Okay, so now you want to do the same idea now, but now see how I'm using a different h value here, and see how much closer, see how much smaller it's getting, right? It's getting very, very close to 0 because it's just getting smaller and smaller and smaller, right? So now when I copy this exact process and I try to find the average velocity again, right, I'm going to be using, right, s of 1 plus h minus s of 1 all over 1 plus h again, minus 1. And then doing this exact same process, but now my h value is going to change. So in here, I'm going to put s of 1 plus 0.01 minus s of 1 all over 0.01. In other words, this is s of 1.01 minus s of 1 all over 0.01. Okay, and now I want to plug in. So this is going to give me, this is going to give me 3 times 1.01 squared plus 1 minus, make sure you use parentheses, 3 times 1 squared plus 1, and then all over 0.01. Okay, and then when I compute this, this gives me 6.03. Okay, and then I'm not going to do it again for part C out, but it's the same idea, except now my h value is getting even closer to 0, right? It's getting even smaller in this case because it's 0.001. And so the average velocity here you would get is 6.003. So let me just write that down. So when you actually do this out, you should get that this is approximately 6.003. All right, and so now in part D, it says to estimate the instantaneous rate of change at t equals 1. All right, so as you can see, right, we considered, looking at here might be a little bit easier for you to see. So let me just highlight this in pink or something. Okay, when we're looking at computing the rate of change, the average velocity between 1.1 and 1, right? We did that in part A. And then in part B, we computed the average velocity between 1.01 and 1. And then in part C, it was between 1.001 and 1, right? And so as that h value was getting smaller and smaller, it was shrinking, right? As that distance between the 2 points, 1 plus h and 1, was getting smaller. all right, we could see that what was happening is the average rate of change, or in other words, the average velocity, was approaching 6, right? I think we would agree with that, right? Because in part A, we get 6.3, part B, it's 6.03, and then C, it's 6.003. So as the h value is getting smaller, it seems like the average velocity is approaching 6. And so my estimate for the instantaneous velocity at t equals 1 is 6. All right, so let's write that down. So as the h value is getting smaller, i.e. distance is shrinking, between t equals 1 and t equals 1 plus h, we see that the average velocity is approaching 6. So we estimate instantaneous velocity is 6. At t equals 1. Okay, so yeah, that's my estimate there.